Objectives. In previous sections it was stated that, 1. Among the different methods of synthesizing nanosized powders, flame synthesis has by far the highest possible production rate, and it is the only method in which scale up to high production rates has been demonstrated. 2. Hard agglomerates are usually formed during aerosol processes, particularly in flames, because of the high number densities and steep temperature gradients. 3. Nanophase materials are very susceptible to contamination. 4. Contamination and the presence of agglomerates destroys the properties of the nanophase bulk material. And 5. The encapsulation process could be an effective solution to control agglomeration, and to protect the primary particles from contamination. The objectives of this work are to demonstrate the applicability of the particle encapsulation method to the production of high purity, unagglomerated nanoparticulates of tungsten, W, and tungsten-titanium alloys, WT, by flame synthesis. Develop a Monte-Carlo method to model particle dynamics in multi-component aerosols. Apply the Monte-Carlo method to study the processes occurring in two-component aerosols in order to understand the encapsulation process and evaluate approaches to optimize the encapsulation process as a solution to the particle contamination and agglomeration problems during the formation of nanosized powders in flames. Specific objectives. In order to accomplish these objectives, several specific tasks must be performed. Apply the particle encapsulation methodology to produce high purity, unagglomerated nanoparticles of W, T, and WT by flame synthesis. This step requires selecting the appropriate reactants for the production of W, adapting the existing burner for the production of W, producing 20 grams of nanosized W and WT powder of optimal quality, consolidating produced powder into bulk cylindrical pellets. Identify and describe the variables and mechanisms controlling the encapsulation process. Formulate the mathematical equations that govern the physical processes occurring in flames and in multi-component aerosols. These processes include nucleation, condensation, and coagulation. Establish an appropriate methodology to solve the mathematical model in terms of the variables of interest, particle size distribution and composition. Validate the method of solution by comparing with analytical and experimental results available for simplified conditions. Apply the mathematical model to a simplified flame configuration, where the general equations reduce to their simplest form. The simplified configuration is equivalent to steady-state systems where gas phase precursors react in 1D flame. Describe the process of encapsulation under different conditions. Identify the conditions that will inhibit or promote effective encapsulation. Prescribe optimum operating conditions for the production of unagglomerated nanosized particles.